Hello, curious minds, and welcome back to the channel where we unravel the deepest secrets of the cosmos. Today, we're tackling one of the most fundamental questions you could possibly ask. Why do things have mass? It sounds simple, almost childish, doesn't it? We know that a planet has mass, a person has mass, even a single grain of sand has mass. We feel its effects every single moment of our lives through the force of gravity. But what gives matter its substance, its heft, its very resistance to being moved? For centuries, this question was a complete mystery. Scientists like Isaac Newton could describe gravity's pull on mass with breathtaking precision, but the origin of mass itself remained an elusive ghost in the machine of reality. The prevailing assumption was that mass was just an intrinsic, built-in property of a particle, like its charge. An electron has mass simply because it's an electron. But as our understanding of the universe deepened in the 20th century, this simple answer began to fall apart, revealing a puzzle that threatened the very foundations of physics. The problem became glaringly obvious with the development of the Standard Model of particle physics, our grand theory of almost everything. This incredible framework beautifully described the fundamental particles that make up our universe and the forces that govern their interactions. It was stunningly successful, but it had a colossal flaw. According to the purest form of its equations, all fundamental particles should be massless. They should all behave like photons, the particles of light, zipping through the cosmos at the ultimate speed limit. But we knew this wasn't true. We had discovered particles like the W and Z bosons, which carry the weak nuclear force, and they were incredibly heavy, almost 100 times more massive than a proton. The theory was brilliant, but it was clashing with observed reality. The universe clearly wasn't massless. So, how could this be? How do particles acquire mass? The answer, proposed in the 1960s, was revolutionary. It suggested that mass isn't an inherent property at all. Instead, it's a property that particles acquire through their interaction with an invisible, omnipresent energy field that permeates every single cubic millimeter of space, even the most perfect vacuum. This is the Higgs field. Imagine this field as a kind of cosmic molasses or thick, invisible syrup filling the entire universe. Now, picture different particles moving through this syrup. Some particles, like the photon, are completely unaffected by it. They don't interact with the Higgs field at all, so they slice through it without any resistance, allowing them to travel at the speed of light. Because they feel no resistance, they have no mass. Other particles, however, do interact with this field. As they try to move through space, the Higgs field drags on them, creating a resistance to their motion. This resistance, this stickiness, is what we perceive as mass. The more strongly a particle interacts with the Higgs field, the more it gets bogged down, and the more massive it is. The top quark, for instance, interacts very strongly, making it the most massive fundamental particle we know. An electron interacts much more weakly, giving it its tiny mass. A famous analogy helps to visualize this. Imagine you're at a crowded cocktail party. The room full of people represents the Higgs field. If you're a nobody, you can walk straight through the room from one side to the other with little trouble. You are like a massless photon. But now, imagine a very famous celebrity enters the room. As she tries to walk across, people cluster around her, wanting to talk to her and get an autograph. Her movement is impeded. She gathers a crowd that makes it harder for her to accelerate and change direction. This resistance to movement from the crowd is analogous to her gaining mass. The celebrity herself hasn't changed, but her interaction with the field of people has given her inertia. This is precisely the idea behind the Higgs mechanism. And just like any other fundamental field in physics, the Higgs field has an associated particle. It is an excitation, a ripple, a concentrated bundle of the field itself. That particle is the legendary, the long-sought, the elusive Higgs boson. Finding it would be the ultimate proof that this incredible theory was correct. It was the missing key that could unlock the origin of mass and complete our picture of the universe. The idea of an all-pervading field giving mass to the universe was a stroke of genius, but for nearly half a century, it remained just that, a brilliant, unproven theory. Proposed in 1964 by a group of physicists including Peter Higgs, Francois Englert, and Robert Brout, the concept was mathematically elegant, but it made a very specific, testable prediction. If this Higgs field existed, there must be a corresponding particle, the Higgs boson. The problem? The theory didn't predict what the mass of this boson would be, only that creating it would require colossal amounts of energy. Finding it would be like searching for a single, unique grain of sand on all the beaches of the world. The quest for the Higgs boson became one of the most ambitious, expensive, and monumental scientific endeavors in human history, culminating at one extraordinary location: CERN, the European Organization for Nuclear Research, home to the Large Hadron Collider, or LHC. The LHC is an almost mythical machine, a testament to what humanity can achieve when it unites in the pursuit of knowledge. It is the largest and most powerful particle accelerator ever built. Buried 100 meters beneath the Franco-Swiss border, it's a 27-kilometer ring of superconducting magnets and accelerating structures, cooled to a temperature colder than outer space, a mere 1.9 Kelvin above absolute zero. Inside this ring, two beams of protons are accelerated in opposite directions to 99.99991% the speed of light. This gives them immense energy. Then, at 4 specific points along the ring, inside gigantic detectors like Atlas and CMS, each the size of a multi-story building and packed with millions of sensors, these beams are steered into a head-on collision. The goal is to recreate, for a fleeting instant, the unimaginable energy densities that existed a trillionth of a second after the Big Bang. According to Einstein's famous equation, E equals mc squared, energy can be converted into mass. By smashing protons together with enough energy, scientists hoped to provide the raw power needed to forge a Higgs boson from the vacuum of space. But here's the catch: you don't just see a Higgs boson. The particle is fantastically unstable, surviving for less than a septillionth of a second before decaying into a shower of other, more familiar particles. So, scientists weren't looking for the Higgs itself, but for its unique decay signature. Imagine setting off a specific, never-before-seen firework in the middle of a massive, chaotic fireworks display. You can't see the initial firework, but you know it's supposed to explode into exactly 2 red sparks and 1 brilliant one. The job of the detectors was to track every single particle emerging from trillions of collisions per second, measuring their paths, energies, and charges, and then to sift through this mountain of data, looking for that one specific combination, that unique signature of decay products that could only have been produced by a Higgs boson. It was a statistical nightmare, requiring a global network of computers and thousands of physicists poring over the data for years. The nickname, the God particle, coined by physicist Leon Lederman for a book title, captured the public's imagination, though most physicists prefer not to use it, feeling it overstates the particle's role. Yet, it undeniably highlighted the fundamental importance of the search. Then, on July 4, 2012, the world held its breath. In a packed auditorium at CERN, the leaders of the 2 main experiments, Atlas and CMS, presented their findings. They showed plot after plot, each revealing a small but statistically significant bump in their data at an energy level of around 125 giga-electron volts. This bump was the telltale signature they had been hunting for. It was the shadow of the Higgs boson. The room erupted in applause. In the audience, a tearful Peter Higgs, now an elderly man, finally saw the theory he had co-developed nearly 50 years prior confirmed in spectacular fashion. It was more than just the discovery of a new particle. It was the final, triumphant validation of the standard model of particle physics. The missing piece of the puzzle had been found, cementing our understanding of the fundamental fabric of reality. The discovery of the Higgs boson is a monumental achievement, a cornerstone of modern physics that explains the very substance of our world. This discovery is a profound testament to human curiosity and our relentless drive to understand our place in the universe, confirming that the world we experience is built upon a deep and elegant set of physical laws. What do you think is the next great scientific mystery humanity should focus its efforts on solving? Subscribe for more mind-bending science, and we'll see you in the next one.